Okay, so today I'm going to continue revealing this connection between functional inequalities and mixing times. But I promise it's the last time. So tomorrow, on the next lecture, we'll do some geometries and things that are maybe easier to follow than functional inequalities. Maybe just a quick recap about functional inequalities. So we saw two yesterday. The first one was Poincaré, which controls the decay rates of variance. Right? It's exactly the inequality that you want to study if you want to understand at what rate the variance decays along your semi-group. And it's the following inequality. So you have this constant, the optimal constant was denoted gamma. And you get the variance under the stationary measure, and this was less than the Dirichlet form. And you want this to be true for every f on your state space. Okay? So again, this always holds. You can always take gamma equals 0, and this will be true. The point is that you want to find the gamma which is as large as possible for which this holds. Why do you want gamma to be as large as possible? Because gamma will be the rate at which your variance decay, and you want that to be. You want the decay to be as fast as possible to get good bond on mixing time. Right? Okay, so we saw that this was not very, does not give a very sharp bond on mixing for example, for our toy model, this random walk on the cube. So we replaced variance by entropy, and then we got this new inequality, this modified log Sobolev inequality. So this is the inequality that controls entropy decay. And this was an inequality that looks roughly the same, except that the variance is replaced by the entropy. And here we get this nasty quantity. So it's the Dirichlet form, but between f and log f. So it's not very pleasant to work with this. You know, when you want to study this object, it's very nice, this one, because it's a quadratic form, right? We saw that because of this quadratic nature, we had a nice characterization of this as an eigenvalue. Right? Here you lose this completely. It's very much nonlinear, non-quadratic. So it's very bad. And so that's why today we are going to look at a new inequality, which is better behaved, and it's called the log Sobolev inequality. So you don't have this modified version. It's really the right inequality that you should consider instead of this one. It's not clear what it controls. I will try to answer this later. The inequality looks like that, so it's still something that controls the entropy. Right? But now you want to have something that is quadratic here, right? So why not? Looking at this, that would be much better, right? That would make our life much simpler. So if you think a minute about this, this is not the right inequality. For stupid reason. Right? So all of this you want for every f, maybe every f positive. Because entropy is for positive functions. A stupid observation is that if you multiply f by a constant lambda, then this is multiplied by lambda square and this also, so it's homogeneous, right? Here, if you multiply by lambda, both terms are multiplied by just lambda, so it's homogeneous. But here, you have lambda square and lambda, so it's not the right inequality. So let's put a square. Okay. So that's the log Sobolev inequality. Sometimes, if you don't like this square here, you can remove it and just put square roots here. Because we want this for every function, it's just the same. Okay, so that's log Sobolev inequality. But so far, in the way in which I introduced it, it's not clear at all that this has any relation with your Markov chain. Right? It's just the inequality that you would like, that would be more, that would be nicer to work with than this one, because you then have a quadratic form. But it's not clear at all that this is an object that is interesting for your semi-group. Okay? So let me convince you that this is interesting by looking first at the simpler case of diffusions. Okay? So now you take the state space to be Rd, and you start from a stationary measure which you can put under this form. So pi dx would be like that. And you run this Monte Carlo Markov chain, this continuous version of Monte Carlo Markov chain to simulate from pi, which is just this diffusion. Right? So dxt is minus the gradient of u xt dt plus square root of 2 dB. Right? Okay, so this is just the Langevin equation. It's a famous diffusion. Okay, and the stationary measure for that under Mild assumption will be this. Okay, so it's a nice Markov process, and you can look at the generator maybe. So the generator will just be the you have the Laplacian apply to f, and then you have this scalar product between the gradient and the gradient of the potential. Okay, and then you can, once you have the generator, you can compute the Dirichlet form. Remember, this is just a scalar product between f and minus Lg. You can then do a bit of integration by parts, and you will realize that this Dirichlet form has this very nice form. Okay, it's a very simple object in this case. Okay, so why are diffusions much simpler than our discrete objects? Because of a stupid thing which is very important, and that's actually the main motivation for me today, is to present you this so-called chain rule. So stupid rule that you have learned in high school, but I didn't know about it, and then I realized in January that because of this, the cutoff problem was much simpler for diffusion. So the chain rule is simply that when you want to differentiate the composition of two functions, it's simply have this simple rule. Right? It's completely stupid. Right? And you can apply this here, and what you'll get is the following: that so. This nasty Dirichlet form f log f that we have in the MLSI, when you plug this here, when you replace g by log f, and you apply this chain rule for computing the gradient of log of f, what you'll get is that this is the same up to a factor 4 as this. Right? If you have a gradient of the log, then it's just like gradient of f divided by f. And this, you will have gradient of f divided by square root of f and gradient of f divided by square root of f. So the two square roots will come together, and you have this magic identity. Okay? Of course, this is very specific to the setup of diffusion. There is nothing like this rule in the discrete, so there is no hope to get this identity in the discrete. Right? But this tells you that, in fact, for diffusion, this is exactly the same as this, except that there is a factor 4 somewhere. Okay. So for diffusions, this. So that's why yesterday when I presented this modified Log-Sobolev inequality, people told me, why do you call this modified? In the continuum, there is no distinction between those two inequalities. They are exactly the same thing up to factor 4. But and because Log-Sobolev inequalities were discovered in this setup, not so many people realize that those are actually two different notions. In fact, right? You only see that in the discrete. Okay, I come from the discrete world, so for me it was clear that those are different, and I was actually very surprised when I've learned that these were the same for diffusion. Right? So we come from different backgrounds, but this identity has remarkable consequences. It's one of the main reasons why diffusions are so easy to work with in terms of mixing times, and as you will see, also for cutoff. This chain rule makes cutoff much easier to study for diffusions. And I'm interested in discrete Markov chain, so I will try to explain today how you can still restore a chain rule in the discrete and make things like that work in an approximative way. Okay, and we'll use that to understand cutoff for discrete chains later. But so that's the plan. Okay. So in particular, this means that for diffusions, this log Sobolev inequality with constant beta is the same as this modified log Sobolev inequality with constant 4 beta. Okay, it's exactly the same inequality. In terms of constant, I told you that I would call the optimal constant there, I would call it gamma of t, alpha of t, beta of t, the largest value. So in terms of optimal constant, this means that the optimal constant in the log Sobolev inequality, if you put a 4 in front, it's exactly the same as the optimal constant in the modified log Sobolev. Okay. Again, this is only true for diffusion. Okay, no. So that was just an aparté. Let me now come back to the discrete world and study this inequality, this log Sobolev inequality in the discrete. Okay. This still makes sense in the discrete, even though you don't have this connection, so it's not clear at all what this means in the discrete. But let's look at this inequality.
So you don't have t, no?
Yeah, right. Okay, maybe the optimal constant. Okay, I need to distinguish. In practice, you establish this inequality for a given Markov chain for a constant, the best constant you can work with. But sometimes this constant is not the optimal one. Right? It's far from the optimal. It's the one for which you can establish this inequality. So I need two different names for the constant you are working with in your inequality and the optimal constant in this inequality. But okay. Okay, so now let's look at this log Sobolev inequality in the discrete. What does it mean? It turns out it's quite remarkable and quite surprising, but this controls something. It has a natural interpretation for your semi-group, just like MLSI controls entropy and Poincaré controls variance. This controls something that you have already heard in Massimiliano's talk. It's the hypercontractivity. Okay, so I'm going to explain that now. What is this hypercontractivity? So to explain that, let me recall that this transition matrix T, now I'm back to the discrete world, so I have a transition matrix T. Remember that T can be viewed as an operator. Right? T is acting on this nice Hilbert space. And when I write L2, it's really L2 of X pi. Right? And it's actually a contraction on this space. Contraction in what sense? Well, if you compute, maybe let me remind you the definition. Tf of X is this. Right? So now if I put squares everywhere, I want to compute the L2 norm. I put squares here. And then I get an inequality just by Cauchy-Schwarz. Like this. Okay. And now I'm going to sum over all x against the stationary measure. So if you integrate this with respect to pi, on the left side you get exactly the L2 norm of Tf squared. And on the right side, by stationarity, this is also exactly the L2 norm of F. Just because sum over x, Txy is pi y. Okay, by stationarity. So, and this is completely general, right? If you have a stochastic matrix and you look at it on the right Hilbert space, where you weight by the stationary measure, you get a contraction. And the same argument would work, of course, for any p larger than 1. Right? You are just using Jensen here. So any transition matrix is a contraction on the right LP space. Okay? Okay, so can you do better than this inequality? Well, not really, because when you take f equals 1, say, then you have equality. You have equality when f is constant. So you cannot really improve this. And yet, there is this hypercontractivity, which tells you that, so this would be contractivity. T is a contraction, in the sense that it reduces the L2 norm, but you cannot hope for a better constant in front than 1 because of this. Hypercontractivity still says that you have a contraction in a much stronger sense, and this sense is you won't play with the constant in front, you are going to change the 2 here. Okay. So it's just the property that you can take a larger exponent here. By the way, I wrote T here, but the same, everything works for any stochastic matrix, so in particular also for PT. Right? The only thing I have used is that T is stochastic here, and then that pi is stationary for your operator. So this is also true. And what we will see is that this inequality remains true even if you increase the exponent. You take something larger than 2. And the interesting fact is that Q is larger than 2. Okay? So it tells you that this semi-group is regularizing your function very much, in the sense that if you start from a bound in L2, after a small time, your function will be controlled in LQ for Q larger than 2. Right? So your semi-group is smoothing the function. Okay. Now the amazing fact is that this not only the Q will be larger than 2, but it will grow with time. It will improve with time. Right? The Q, it will grow to infinity exponentially fast. So this Q is in fact a Qt, and it's growing exponentially with T. Right? So this means that you are running your dynamics, and as time goes by, your function PTF becomes more and more regular, right, in this sense. And yeah, so that's hypercontractivity. Now let me formalize this in a theorem. From now on, all my chains will be reversible. For simplicity, versions of this theorem exist for non-reversible chains, but my life will be easier with reversibility. Then the following are equivalent. So you have this log Sobolev inequality. For all f on your state space. And two, you get this hypercontractivity statement. One plus exponential of 4 beta t. So you see this is always larger than 2, and it's going exponentially with t. It's less than f2 for all f and all t. Okay, so that's the statement. And again, it's quite surprising that this inequality, which for us just came out of this analogy with diffusion, right? The fact that you have this identity makes this inequality naturally appearing for diffusion. If you look at it in the discrete, you get this nice characterization. Okay, so here is a sketch of proof. It's not very interesting, the proof. I just want to give you the key ID, then it's just computation. If you introduce this function f of t, which is just this, it turns out that this function, if you differentiate, you can compute the derivative. It's a nightmare, so I won't do it on the blackboard, but you can look at the notes if you wish. So if you compute f prime, you will realize that the condition here, the condition 1, is exactly what you need to get that phi prime of t is non-negative, non-positive for all t. Right, so this statement essentially says that this function is decreasing with t. Now look at the value at time 0. At time 0, this p0 is the identity, and this is exactly 2. Right, so the fact that this is decreasing implies this. So that's the idea. Then it's just a matter of computing things, but. And as usual in those, just like in the Poincaré and the MLSI theorem, right? Beta here is any constant, and you have this equivalent. If you want to prove, if you can prove log Sobolev for a certain constant beta, then you can deduce hypercontractivity with this exponential rate of growth of your exponent q, right? And vice versa. Right? So of course the optimal constant, this inequality becomes interesting when beta is large. So you really want the largest possible beta for which this holds, and this I will denote by beta optimal or beta op. Okay. Okay, so it's a miracle. So this hypercontractivity property is a very strong property. We'll see in a minute that it's much stronger than this entropy decay property. It's a very strong regularization property. It's a miracle that for diffusions, those two phenomena are the same. The hypercontractivity property is the same as the fact that you have exponential decay of the entropy. Right? It's not at all obvious because those are two genuinely different phenomena in general. But for diffusion, they are the same thing. Okay, so now I just told you that hypercontractivity is in general a stronger property than entropy decay. So let me formalize this. So you see, for diffusion, we had this nice identity which makes log Sobolev and modified log Sobolev equivalent. In general, there is only one implication that remains valid, and this means that you only have one inequality here. The inequality is the right one, so it's okay, so this is always true even in the discrete. This does not require the chain rule. So you always have this, but in general, you don't have the converse inequality. So in particular, if you have LSI for a certain constant beta, then you do have an LSI with constant 4 beta, right? So half of this relation works. Right? Or in terms of optimal constant, this means that the optimal constant in your log Sobolev inequality gives you a lower bound on the optimal constant in the modified log Sobolev. Okay? Okay, so let me prove this. It's just one line. And the proof is important because then we'll try to repair the chain rule based on this proof. Okay. So maybe it's a good point to remind you what this Dirichlet form is. So this is just, there is a factor 1/2 in front. And you have this. Okay, so here I'm using the reversibility to write this in this symmetric form. Right? Remember, the Dirichlet form of Fg when you have a reversible chain is really a difference of F times difference of G. You should really think of the formula I wrote for diffusion. It was the Dirichlet form was integral of the gradient of F, gradient of G. That's exactly the discrete version of that. And this is always true when you have a reversible chain. Okay, so that's essentially the definition of the Dirichlet form. Okay, and we like to compare that to this. So we'll do a series of inequalities. We would like to, in the end, get this with a 4. Right, so maybe let me explicitate the definition of this. We get 4 over 2, and then sum over all xy. Just like this, px dxy, and then square root of fx, and square root of fy squared. Okay, so you want to argue that this is always at least this. Okay, so what I'm going to do is simply try to write this under this form. Right, so I'm going to pretend that I really have this. And then correct this expression so that this becomes really this. So I will have a correction function, and this correction will be a certain function of this. Right? And what is this f? Is whatever you have to put so that this becomes equal to that, right? So you compensate, and you realize that this is this. Times r. It's just simple algebra. It's you can define f as a function that allows you to change this into this. That's what you get for f. Okay, so far I did nothing. So you see, I would like to argue that this function here is always at least 4, and I'm done. Okay. But that's basic. You differentiate f, and you realize that f is has a minimum at 0, which is equal to 4. So in fact, which is very easy, f is an even function. Increasing on 0 infinity, and because it's even, it has to be decreasing on minus infinity 0. Right? So the minimum is at 0. And if you compute the value at 0, right, just do a Taylor expansion at 0, and you'll get 4. Right? So that's it. Okay. Okay, so maybe it's a good time to look at the example. So it turns out that so there are chains for which, discrete chains for which this inequality is very much not achieved, right? So this constant can be, the ratio between those two constants can be arbitrarily small if you consider any possible Markov chain, right? So which really means that this hypercontractivity phenomenon is much stronger than the entropy in general. You cannot get one from the other. But if you look at simple examples, then it turns out that those are of the same order. So let's look at our two examples. Example 1. I won't do the computation, but the cycle is simple enough so that you can compute things, and you'll realize that this beta is of the same order as alpha, which remember was n to the minus 2 for the cycle. And our example 2 is, of course, the n cube. In that case, you can actually compute beta exactly. It turns out to be exactly 1 over n. Which means that in that case, if you remember, this alpha was 4 over n. So in that case, I should put maybe optimal everywhere. It's really the optimal constant. And we saw that, so this is one case where you have equality in this inequality, just like for diffusion. Right? It's not a diffusion here, but it turns out that in this case, you still have this nice result that hypercontractivity has the same exponent as the entropy decay. Okay, so this looks like a stupid example where you can do the computation easily. It relies on this the same idea as for alpha. I don't know if you remember, but I told you yesterday that the entropy has this nice tensorization property. The entropy of a product measure is the relative entropy of two product measures is just the sum of the individual entropies. The hypercube is nice because the coordinates are independent. So this tensorization property reduces the computation to just the case where n equals 1. Right? And the hypercube in dimension 1 is just a 2-point space. So you can do the computation there exactly and compute this exactly. And this computation was done in the 70s. It's a famous inequality. It's called the Bonamy-Beckner inequality. Okay, maybe some of you have heard about this. I'm sure at least one person in the audience has heard about that. It's a famous result, even though, you know, this is just computing the Log-Sobolev constant of a very simple model. This has huge consequences for the analysis of Boolean function. It's actually the starting point of an entire theory of influences and sharp threshold for Boolean functions. So it's really a huge inequality there in Boolean analysis. So there are entire books that start with just this simple fact. Right? It's not really the Log-Sobolev point of view that is interesting. It's of course this hypercontractivity property of the semi-group. And from there, you get a lot of nice consequences. So even in our simple toy model, this is an important inequality. Okay. Another interesting thing maybe is that, you know, there is a certain way in which you can take limit as n tends to infinity in the hypercube. And in a certain sense, the limit that you can get the Gaussian measure out of a limiting procedure for the hypercube. And so you can get the Log-Sobolev inequality for the Gaussian, which is the one that Massimiliano used, as a limit from the Log-Sobolev inequality for the hypercube. So this is really, this toy model computation is actually quite important in theory. Okay. So now I want to convince you that you know, this inequality can be reversed. Okay, that even though we are working with discrete chains, we still have a chain rule in an approximate way. Okay, and that will be useful again because for the cutoff, we'll need to do exactly the same kind of reasoning. We'll first prove cutoff for diffusions and then try to, from that, to project the proof to the discrete, and we'll need exactly this type of argument. Okay, so to understand how to reverse this inequality, maybe it's good to look at this proof here. You see, the difference between this term and this term is precisely given by this function. Right? And the reason why you had an inequality like that is that this function is always at least 4. Okay, so the obvious thing to do if you want to reverse this inequality is to look at what's the maximum value of this function. Right? Unfortunately, it's plus infinity. Right? So there is no way to reverse this. Right? If you want an inequality like that to hold in the other direction with constant, and you want it to hold for every function, it cannot work simply because if you take a function for which this thing here becomes higher and higher on a particular edge, then this quantity will become higher as large as you want, and so in the end you will have something that is much larger than this. So in general, it's not possible to reverse this. So there is no hope to reverse the inequality, maybe this one. Let me call it star. Uniformly in F. Uniformly in F. But the key thing is that it's this impossibility is only because you want something uniform in F. Right? If you fix a function F, then you can reverse this. We at least have this. So let me start with this one. So this is always true. But this is at least this. Right? And this argument here tells you that it's at least f of r times this. And what is r here? R will depend on f, it cannot be uniform. R is simply the maximum value of this ratio. Right? So in other words, it's the Lipschitz constant of log of f. Right? It's how much this function log of f can vary when you make a transition. Remember that here we're looking at pairs x, y, which are neighbors in the state. Right? So you can reverse this inequality, but the price that you will pay will depend on how regular your function f is. Of course, your function in general can be as irregular as you want, so in general this can be made as large as you want. But, okay.
Why you say it's the Lipschitz constant?
Okay, maybe, yes, that's good. That's a good question. I should, yes, let me make this more precise actually.
Okay, for the chain.
Yes, but it's important to, if you ask the question, I'm sure many people want clarification. So let me say that I'm in the setup where the chain is reversible. So I can define a natural distance of my state space. And it's really the graph distance for the diagram of your chain. Right? It's a very natural thing to do. You define the distance between two states to be the number of steps that your Markov chain needs to make in order to reach y starting from x. Right? So just minimum n such that Tn xy is positive. Right? But really, think of you have your Markov chain, you can define a graph on this Markov chain by saying, by putting an edge between two states if you can jump from one to the other in one step. This gives you a graph, and then look at the graph distance, number of edges that you need to cross. This is this. Okay, it's a very natural. That's what when you consider a particular Markov chain, you always draw this diagram, and then that's really the distance in the usual sense. Okay, and now this gives me a metric space. Now my state space X is a metric space, so I can use the vocabulary of metric spaces. For example, I can define the diameter of my space, right, to be a maximum. Right? This makes sense. And I can also define the Lipschitz constant of a function. Right? It will be the supremum over all x, the maximum because it's finite. X different from y, f of x minus f of y, divided by the distance. But this is the same just by the triangle inequality as the maximum over all neighbors of just f of x minus f of y. Okay. One inequality is trivial because I'm looking at the maximum on a smaller set. Okay. But the other inequality follows just from the triangle inequality. If I know how to control the variation of f on any edge, then I know how to control the variation along any path. Right? So that's really the same. So it's the Lipschitz, this Lipschitz definition makes sense just because I have a metric space. And now I can define this Lipschitz of log f. Right? It's the maximum over all possible. You look at all neighboring states in your state space and you look at log of f of x minus log of f of y, so it's really this. Right? And that's the quantity that appears here. Okay? Okay, so really, again, we proved something for diffusion. You had an identity because of the chain rule. In the discrete world, you still have a version of this identity, but with a cost to pay that depends on how regular your observable is. Okay, that's the philosophy. And this is a very general principle. It emerged quite recently, actually, but I found many applications of this vague principle, which is that whatever is true for diffusions, thanks to the chain rule, remains true in the discrete up to a price that depends on the regularity of the observable. And it's really just this, but it will give you several interesting consequences in there. You will see in the next lecture. Okay, so from this you can actually deduce the identity for diffusion, because for diffusion you are making only local moves. So this quantity becomes arbitrarily close to 0 actually. And when r tends to 0, we have seen that this tends to 4. Right? So you can see this. You can see the identity between this and this for diffusion as a limiting version of this for infinitely smooth function. Right? In the discrete world, the functions are not smooth, so you have to pay a price. Okay. Okay, so I still want to reverse the log Sobolev. I would like to deduce modified log Sobolev, log Sobolev from modified log Sobolev in the discrete. But so far I cannot, because this is not uniform in F. Okay. And nevertheless, it turns out that you can reverse the it came as a surprise to me. It's a recent result, but it turns out that MLSI implies LSI, which is the converse of what we saw before, up to a certain cost. But this is very surprising for people working in the discrete. It came as a surprise that you can actually convert an MLSI into an LSI just like for diffusion, but you have to pay a price. And what is this price? Again, for reversible chains. So the usual inequality is this one. This is always true. And my claim is that you can reverse this. So you can upper bound this in terms of beta up, but you have to pay a price. Okay, so there will be a universal constant, and then something that measures the sparsity of your state space. So log D. What is D? D is this quantity. You look at two neighboring states, and you look at the probability to go from one to the other, and you take the max over all inverses of those. Okay. It looks like a complicated quantity, but think of it as, look at simple random walk on a graph. Simple random walk on the graph, the transition probability are just 1 over the degree. So 1 over this is just the degree, and you are looking at the maximum value of this, so it's just a maximum degree in your graph. Okay. So think of this really as measuring the sparsity of your chain in the sense, how many neighbors does each state have. Right. It's roughly the maximum degree of the graph. It's exactly this when you look at simple random walk. In general, it's a weighted version of this, but you should really think of this as being small when your random walk is local, in the sense that you only have very few neighbors to which you can jump to. Okay, then this is small. Okay, and this is universal. Maybe 16 or something like that. Okay, again, this came as a surprise. It has nice consequences for mixing time, but the most important thing for me, the reason why I'm presenting this, is that it's an instant of this new general principle that whatever is true for diffusion, so for diffusion you have equality, remains true for discrete chains at a certain price, and this price is always this mysterious quantity log D. And you will see that also for cutoff. So I want to present this just as a first instance of something very general that we'll use later. Okay. Yes, but yes. This makes my life simpler, but basically everything I present today works for non-reversible chains. It's less pretty, so you will lose constant. Even in this inequality, you lose a factor 2, and here you lose factor 2 as well. Let's keep things simple. And
Can we define Lipschitz for non-reversible chains?
yes, that's a good point. So you don't really need. You can take a. Right, you see in this argument, I just erased, but in the argument where I had this function f of log of f of x over f of y, what you really care about is the maximum value of this, not the maximum value of not the absolute value. So you just need to define this Lipschitz like that, and that's fine. Yeah. Okay, but let's keep things simple. I mean, it's nicer to work with a symmetric state space. Okay. So the proof I'm going to present, this is a result, it's a joint work with Pierre Youssef, and it's a result from 3 months ago only, right? So log Sobolev and modified log Sobolev, those were topics that are classical, that were invented several decades ago. But this is very new, and the approach you will see is very simple. It's basically a consequence of this, but we need to work a bit. Okay, so what's the problem with this this reverse thing, right? So when you want to prove those functional inequalities, you must, if you want to have a bond on alpha or beta, you need to prove those inequalities for every function f. Right? And if you want to deduce some knowledge about MLSI to this LSI, you need to be able to compare this one to this one, right? So that's what this inequality gives you. But you need to do so for every f. And that's a problem, because if you know that if you look at every possible f, then this will blow up. Right? This is the regularity of your function. There is no bound on that. This can become arbitrarily large. Right? So it seems like a real problem here, because we want to prove those things for every function. Those are functional inequalities. Now here is the stupid observation, that in fact you don't really need to prove this for all functions, just for one function. The one that actually realizes the equality. Of course, you don't know what it is, but that's the one that you really care about. So in fact, this R here, that you really want is the one, it's this Lipschitz regularity of the optimizer in this inequality. That's the one that you really want. And this constant, this Lipschitz regularity, is precisely this one. That's what we are going to prove. Okay, so it's stupid, but instead of focusing on proving this for all functions, turns out that you just need to prove this for one function, one that nobody knows actually. This extremizer is something completely implicit, nobody knows, but that's the only one you care about, in fact. Okay. So let me rewrite this optimal constant, this beta opt. I told you it's the best possible constant in this inequality. So it's a variational problem, right? It's the infimum over all function f in a certain set of this. Okay, and f is simply the set of functions on my state space which are non-negative and non-constant. Right? You don't want to be dividing by 0. Right? Constant functions, for constant functions, this is 0, this is 0. Okay? And so my claim is that if you can give me the function that that solves this optimization problem, then I know what the constant here is. So if f achieves then I can write the following. So I have beta up times entropy of this particular f will be equal to this Dirichlet form. And now I use my local comparison here. So it will be larger than 1 over f of r times this. And then I use the MLSI. The MLSI works for any function f. So just by the MLSI, it's always at least 1 over f of r times alpha optimum times the entropy of f. Okay, and now you can cancel both terms. Right? On both sides, you have this entropy. My function is not constant, right? I'm minimizing over non-constant function. So you can safely simplify, and you get exactly this comparison between beta opt and alpha opt. Okay, so that will be the plan for proving this. So from this, you can conclude already that alpha is less than f of r times beta out. Okay, and that's the kind of inequality we want to prove. Right? So what we need to do now is estimate the log Lipschitz regularity of the extremizer in this optimization problem. Doesn't look like an easy thing to do because in practice you never know what this where this is achieved. Right? But if we can do that, then we get a bound on this. So the goal now will be to estimate this R, which I remind you is the Lipschitz norm of log of my optimizer to this. Okay, so we need to know a bit more about the optimizers, and here is a simple lemma. Okay, so maybe if the infimum in star is now this, is achieved at an interior point, so in the interior of this, right? So which basically means that your function is strictly positive, you cannot take value 0. Then this function can actually solve a simple functional equality. And this is the equation, so you have L of square root of f plus beta square root of f log of f over the expectation is 0. This should not surprise you. It's actually an instant of what Peter presented just before. It's just, you are maximizing, you're trying to look at the minimum of a function, or at least a local minimum of a function. And then you know that the gradient at this place is 0. That's what this says. You will see in the proof. This is essentially what this says. Okay, good. But, so far, it's not actually clear that this minimum is achieved, and even if it is achieved, it's not clear that it's achieved at an interior point, so we need some care about the rest. So there is a continuation to this theorem. Okay, so maybe I can continue here. So if the infimum is achieved, then you have this. If it's achieved at an interior point. If it's not achieved at an interior point, then actually it's not achieved at all. And we have equality in those two inequalities. So you have for beta is equal to alpha. Okay, so there is this annoying case where this infimum is not achieved, but it's actually a good case for us because in that case, actually MLSI and LSI constant are the same. So it's even better for us. This degenerate case where you cannot find an optimizer is even a good news for us. And even better than that, it's actually equal to twice the spectral gap. Okay. So in general, I remind you maybe that there was a hierarchy between those. This always implies this up to a factor 4, and this always implies this up to a factor 2. Right? So in general, you only have this. No, this. And it turns out that in this degenerate case where the infimum is not achieved, you have equality everywhere, which makes life very simple. Okay, so proof of this lemma, it's basically just what Peter did. So let's compute maybe I'm going to write it in a better way, but I told you you can always remove the squares, the square root, and put a square here, so it's better like that. Like just by a change of variable, I'm going to write it. Okay, and I'm just going to compute the gradient of this. Maybe we should do that together. So what's the gradient of the numerator? Remember, this is just scalar product of f and minus LF. So the gradient of a quadratic form is just the matrix itself. Right? So this is just minus LF. There is a factor 2. Okay. Just like differentiating the square, but in a matrix way. Okay, so let me now compute the gradient of the denominator. So gradient of, we already computed the gradient of entropy of f. Okay, so for the gradient of entropy of f, we saw yesterday that this was simply log of f over expectation of f. Right? But now we have to compute the gradient of f squared, the entropy of f squared, so you get f squared, and you still have to pay the gradient of f squared, so you get 2f. Okay, and from this and this, you can compute now this. Right, so I'm differentiating a ratio. So I will have I'm first differentiating the numerator. I use this formula, so minus 2LF. Okay, and then you differentiate the numerator, so you get minus. Here you get f squared, and it's actually squared. And then this one does not change, and you pick up this quantity. Okay, so maybe. Okay, so you can write it in a simpler way as follows. So it's simply minus 2 over this. So I'm factoring out with this term here. And then what I get is LF minus, if I remove the square, this is exactly phi of f. So it's phi of f. And then you still get twice. So it's plus twice f log f squared over the expectation. Okay, so in particular, if you are on an interior point, then this must be 0, right? But we chose to work with this change of variable that square root of f is replaced by f. So if you replace this f by square root of f, you get this. Right? Right, so at an optimizer, is an interior minimizer of the functional, then the value here will be beta opt, and so you will get the gradient is 0, so LF plus 2f beta opt times the log of f squared over expectation of f squared is 0, and replacing f by its square root gives you this. Okay. Okay, so now the second thing to worry about is if this infimum is achieved at the boundary, right? So it's achieved inside in the set, but not in the interior of the set, which means that it would be achieved at a non-interior point, a function which is non-constant, but which is not strictly positive. So the claim now is that cannot be achieved on f minus this its interior. Okay, so and the reason is the following: it's simply this computation here. So if you take f in this set, then f is non-constant because it's in the set f, but it's not strictly positive. So you know that f of x will be 0 for some x, and it's not constant, so you know that f of y will be strictly positive for some y. And you can always, because the graph is connected, the chain is irreducible, you can always choose x and y that are neighbors such that this is true. Okay, and then you evaluate this expression at x. Right, so this term becomes 0 at x because there is this fx, and fx is 0. So this becomes 0. And now this LF, by definition, it's the sum over all y, and then you look at txy, fy minus fx. This one is 0, and we know that there is at least one neighbor for which this is strictly positive, so this is strictly positive. Okay, so this is 0, this is strictly positive, but there is a minus sign in front, so the gradient is negative. And so it cannot be an optimal because you could then, so the gradient at x, sorry, is negative. So this means that if you add a bit of mass at the point x, so you replace f by f plus epsilon at the point x, and if epsilon is small, this will be strictly less than phi of f. For small epsilon. And so it cannot be a minimizer, right? So it's essentially what Peter did. This, you can express this in terms of tangent cone and the polar cone of the tangent, and you have this. You cannot have this gradient being negative if you want a minimizer. Okay, so the last case that remains is the one where the infimum is not achieved at all. But what does it mean if it's not achieved? So finally, then you can always, it's an infimum, so you can always approximate the value. So we know that beta opt will be obtained as a limit as n tends to infinity of a sequence of evaluation phi of fn, where fn are still in F, right? Okay, but you cannot pass to, there is no point where you can remove the limit. Okay, so it's not achieved, but still you have this. Okay, phi is invariant if you rescale things, because this is homogeneous. That's why we added the square here in this equation to make this homogeneous. So by rescaling, we can assume that the expectation of fn is 1. It won't change the value of phi. And okay, upon extracting the subsequence, we can assume that this sequence converges. So fn converges to some f without log of linearity. Right? Just because of this is enough to get tightness. Okay, but we know that so the function phi is nicely continuous, and we know that there is no minimizer of phi, so this f cannot be in your set. Right? Otherwise, you would have found a minimizer inside. So f must be constant. Right? That's the only way you can be a limiting point of function in f. So you have a sequence of non-constant function, non-negative, and they converge to something which is not like that, then this must be constant. And because the expectation is 1, the expectation of f is 1.
Why cannot just arrive on the boundary? Why cannot just arrive?
So I excluded the case where you have an infimum on the boundary. Right? So it's not possible for this infimum to be. So if this infimum is achieved inside, in the interior of the set, yes, I have this gradient that was this argument here. You can always improve your function if you are on the boundary. So it cannot be true that the infimum is achieved at the boundary. Okay. So it's constant, but its expectation is 1, so it's actually 1. So in fact, I have fn which tends to 1. Good. So I'm trying to compute this beta optimal, but what I'm saying is that this beta opt is obtained as a limit of this objective function here near the function 1. And we saw yesterday that when you look at functions that are close to the function 1, then the entropy becomes just the variant. Okay? So in fact, in this regime, entropy becomes variance. So this optimization problem here, if you replace the entropy by the variance, this becomes just this. Right? So you are back to the Poincare inequality. So it's even better for us if you are looking at flat functions, then all of these log Sobolev things become just Poincare. Right? So phi of fn becomes the same, is equivalent as n tends to infinity, because we are in this regime. You just Taylor expand the logs and everything. Everything simplifies when you are close to 1. You can simplify those expressions here. And so here you will get, so the entropy will become half of the variance. But it was the entropy of the square of fn, so it becomes the half of the variance of the square. But again, if fn is close to 1, then fn square you can Taylor again, and you'll get that it's the same as this up to a factor 4. Okay, and this is so this is always at least 1/2 times the spectral gap, right, the gamma opt. Okay, so the conclusion is that beta opt is always at least 1/2 gamma opt, but this is the opposite direction of what should be true. Right? I told you that you always have this chain of inequalities, so you will always have this for beta opt less than alpha op less than twice gamma op. Right? And this, in this case where you look at functions that are close to constant, you actually have the opposite inequality between this and this, so everything must be identical. That's it. Okay, so now we have a nice equation for this fixed point equation for this extremizer of the log Sobolev function. Let's see if we can extract from that this estimate on the log Lipschitz regularity, and that will be easy. Just write down this nice equation, and you extract from it some regularity. So the last thing we need in order to prove the theorem is the following observation, that if f solves this thing here, so where was my, I erased it. So my equation was this, so L of square root of f plus beta square root of f log of f over expectation is 0, then I know the regularity. It will be at least this universal constant time log d. Right? That's all I need to do in order to prove the theorem. Okay. And what I'm going to do is just evaluate this at a point and see what I get from it. So let's evaluate this identity at any x. Right, so I'm just going to write down exactly what this means. So get sum over y, txy. This is the difference of values of f across the edge. Right, so this is this term. And then plus beta square root of x. Maybe I can assume without lots of generality, just upon normalizing f, I can assume this, right? If I have a function that satisfies this, I just divide it by its mean, and it still satisfies this. Right? Okay, so we have this. And now I'm going to divide everything by f of x. This becomes just 1, and this disappears. And so what I get is this. Txy square root of fy over fx is at most 1. Right, the sum of this 1, because this is stochastic, this gives you 1, minus beta log of x. Right? And this is true at any x. Okay? So it's equal. Okay, remember what I want to do is estimate this log Lipschitz constant. Right? This log Lipschitz constant will be achieved somewhere. There is an edge on which the variation of this function is maximal. I'm going to look at this specific edge. So let me consider two neighbors where this is achieved. So achieving the definition of okay. Maybe let me give it a name. It's this number R that I already used before. So what this means is that I know that R is exactly the difference, right, like that. maybe the other direction. Okay, so there is always an edge for which you have this equality. The set is finite. I'm looking at the maximum over all possible values. So there is a point where it's achieved, and that's the one I'm looking at. And now I use this equation in a very trivial way. I'm going to say that this part here certainly contains at least this term. So you will get a exponential over 2 corresponding to this contribution here. Times this entry, I don't have any control on this. I just know that it's positive because I'm choosing neighbors. So this is positive, and that's where I'm going to use this parameter d. I know that this is always, if it's positive, it must be at least the inverse of d by definition of d. Right? This is the maximum over. It's the inverse of the minimal transition probability. So I know that I have. So I'm going to use this very crude bond. Right? And now I need an upper bound on this. So I don't know much about this function f, but still I can estimate this. I know that the expectation of f is 1. So I know that f will take values that are sometimes larger than 1, sometimes smaller than 1. So I know that log f will change sign. So this minus log f of x, I can bound it by just the maximum value of log f, right? Because I know that this will be positive, and minus the minimum value of log f. Okay, it's a very crude bound, but I don't know much about log f, so that's what I'm going to. And now I'm going to use the fact that I am on a finite state space. I know that this function log, whenever I cross an edge, I pay a factor r at most. And if I do this along a path connecting the maximum value to the minimum value, I know that I will pay at most this. Okay. And at this point, I will need just a very standard estimate that I was planning to prove, but I won't. It's a very standard. There are a couple of bonds on the diameter based on various constants, and one of them is. It's an easy observation. It's always easy to get bound in this direction. What is hard in the log Sobolev inequality is to find lower bound, but upper bound are easy. You just take the right test functions and you get this. So you have this general fact for any Markov chain that the diameter is, the inverse log Sobolev constant is at least the diameter. And so if you plug this here, so this minus beta log of f is at most square root of 2 times r. Okay, and so I replace it here. Remember, this one I estimated like that, so in the end I get this. 1 plus square root of 2r. Okay, and that's the end of the proof essentially, because remember I want to prove that r is at most log of d. This inequality forbids r to be large, right? Okay, you can pass this d on the other side, pass this here, and you get essentially that exponential of r is at most d, so r is at most log of d up to constant that I don't want to compute. Okay. Okay, so again, the result has interesting consequences for mixing times of Markov chains, but really remember this philosophy that whatever is true for diffusions using the chain rule remains true in the discrete world, but you'll have to pay a factor log d, and this log d comes from the log Lipschitz regularity of the observable that you really care about. And you will see this 3 times during the course. We'll apply this to cutoff later. Okay, so that's it for functional analysis. Next time we do geometry and things that are probably nicer to follow. Do you have questions?
So you prove the fact you mentioned?
Yes, I can. 10 minutes, yes. Okay, there are a couple of very simple bonds on the log-Sobolev constant. Again, it's lower bonds, so it's upper bonds on the log-Sobolev constant, so it's easy, right? The hard thing in this inequality is the opposite. Beta is an infimum, so it's easy to prove that it's small, but it's hard to prove that it's large. Here, we want it to be small. So proof of this now. So we have two simple bonds on beta, simple upper bond on beta. So first, 1 over beta is always larger than just because of this. So it's the optimal one. It's always, I'm going to use this stupid thing that it's, okay, so that's the first thing. And here is another trivial bound. Is at most log of 1 over pi mean. Right, so this we know it's already this inequality that is always true. And this one comes just from, you look at this inequality and you plug a test function, and your test function is the one you would think of. You look at the Dirac mass at x. Right, so compute take f to be, so take f to be indicator of x in the LSI. And that's exactly what you get. Well, you get log of 1 over pi x, but then you can choose the best one and you get this. Okay, so it's completely trivial. And from this, you already get this, that 1 over beta up is at least, right? We want to get the diameter here, but now we get this. Square root of 4 alpha opt. Okay, and my claim is that this is always at least square root of 2 times the diameter. So what I really need to prove is an inequality between the diameter and the modified log-Sobolev constant. Okay, and now I have to prove this, and this is an easy consequence of sub-Gaussian concentration, in fact. The result we saw last time about sub-Gaussian concentration of Lipschitz function. Okay, so it's a couple of lines, so we should have time. So now I have to prove this. And then everything is proved, okay? It's a very nice argument. So let me remind you that the modified log-Sobolev constant controls sub-Gaussian concentration. So we have probability that any function on the state space is larger than its mean, plus r is at most exponential of minus r square over 2 times this optimum. Maybe I'm looking at functions that have 0 mean for simplicity. So expectation of f is 0. And also I had this condition that f does not vary too much. So Lipschitz norm of f is at most 1. Okay. For any function like that, we saw yesterday this inequality. Okay. Let me take r to be the maximum value of f. Okay, in this inequality. Then I know that this has a positive probability to happen. Right? This max must be realized somewhere. So I know that this is positive. It's at least the minimum stationary mass. Right? And then we get this. Right? Or equivalently, the same as saying that the maximum value of f is at most square root of 2 alpha opt log of 1 over pi. Okay. But of course, you can replace f by minus f. And then you get the same inequality for the minimum. And with like that. And with the minus. And so when you combine the two, you get that the difference is bounded by exactly this quantity square root 8. Okay. It's true for any function. It's any Lipschitz function. You can control the maximum amplitude of this function, so the maximum minus the minimum. And it's at most this. Right? It's a consequence of sub-Gaussian concentration. There is an 8. Okay, and now that's it because you take f to be. So how do you this is true for any Lipschitz function. How do you get the diameter here? What's the Lipschitz function you take? Huh? F of x is? The distance, yes. Take the distance from any particular origin to x. This is, of course, Lipschitz. The problem is that it's not centered. But you see, I use centered here. But in the end, this conclusion, if you shift f by a constant, you don't change this. So this remains true for, you don't need this condition here. So the maximum value of f will be just this. And the minimum is, of course, 0. So you get this. And then you take the worst possible origin. And that's it. Okay, so now I'm really done. I should first ask if there are questions. Yes?
I have a question about the overall setup. So could you tell us about the possible application of upper bound of alpha with beta? Because for mixing time, you prefer lower bound.
That's a great question. So I told you that, no, in the end, if you care about mixing time, this is really the constant that you want, right? This is not really useful. But I also told you that this is a very bad quantity, very poorly behaved. It's difficult to estimate, and also it's very difficult to transfer results that you know for this form on a particular chain, on a nice model, say the hypercube, to transfer it to other chains. Whereas this is a quadratic form. This, we have many methods to compare this from two different chains, right? If you have a model where you can compute or estimate this, and you have a model that is close to this, then you do comparison of Dirichlet forms, and you get relation between those two models. Right? So this will work for the log Sobolev constant. It will never work for this. There is no comparison theory here because this is not quadratic. Okay. So the idea is that you have a chain for which you know how to compute this, for example, the cube. But this is not very satisfying because you cannot transfer it to any model. So you move to beta. And to move to beta, you need this, this inequality. So you pay a price which is log d. Then you move to beta. And then suddenly this beta, you can transfer it to other models. And you get consequences in terms of mixing time using that. So this quantity is much more robust, and it's always preferable to transfer a knowledge on alpha to a knowledge on beta so that you can transfer it afterwards. So that's how it's actually used to get, I used it to solve certain conjectures about mixing times for zero range processes that were open for a long time. And using this trick, it becomes completely easy to do. So it really has applications.
But it's still hopeless to get cutoff from that.
Yes, exactly. All of this, you see, gives you bounds on the mixing times that at best will give you bounds up to constants. So that's not the way we are going to use it. Still, it's not, I'm not doing this for nothing, right? All of those tools, we are going to combine them together in the end to prove cutoff. But we are going to use those inequalities and curvature in a different way as what people used to do. You don't want to bound mixing time with that. That's not the right idea. We are going to bound, okay, you will see, but we are going to use this material in a different way, but still you need to learn about this material. So it's useful to follow, but yeah.
So you said that the simple random walk on the n cube had two remarkable properties. First one, when you use the modified Sobolev inequality, you get a sharp bound on the mixing time.
Yes.
And you also said that the inequality between beta and alpha is saturated
Yes.
by this model. Yes. Are those two coincidences somehow?
No, yes, they are related. Yes, okay. Yes. It's a model that is very special in the sense. So you know, in all those inequalities, we are doing something terrible for mixing times because we are sort of we want to estimate how the distance to equilibrium in maybe in relative entropy decays, right? And for this, we use a bound which is uniform in the decay rate. So we want to say that it's at most times the value at 0. So this is f of t. You see, and in all those inequalities, the exponential decay is something of this form. But this is very, and you take the k for which this is the best possible k for which this holds. But this is very pessimistic because maybe the curve initially it starts like that, but then it improves a lot, right? And then the mixing time, your bond on the mixing time will be somewhere here, whereas it should really be there, right? But that's the price to pay if you want something uniform. The magic with the hypercube is that this is really, the distance to equilibrium decays really like an exponential minus t, precisely like that, right? So the estimate that you get are exact in this sense, right? Think of the hypercube as really a model where all the distances behave like that, and then all those inequalities suddenly become perfect for this model. Yeah. But again, still, the statement about beta being 1 over n for the hypercube is this Bonami-Beckner inequality. It's far from a trivial thing. It's something that has huge implications in Boolean analysis. So it's, even in this toy model where those notions become trivial, what you get out of this log-Sobolev inequality is an amazing statement. Okay. Okay, so we can have lunch now.